Let's continue on in our titration and consider what happens after adding 25 milliliters of sodium hydroxide. So this is the third point in our titration curve. To find the pH of the solution after adding 25 milliliters of 1 molar sodium hydroxide, we begin by writing the list of major species that you have in the solution before any acid-base reactions happen. And this is the same list of major species that we saw in the most recent example when we had 10 milliliters of NaOH, right? We have acetic acid, Na+, hydroxide ion, and water. Because we have hydroxide ion, it has to react immediately and to completion with the strongest acid that's in your solution, which is acetic acid. The reaction goes through to completion. So this is a stoichiometry problem. Write the stoichiometry reaction and make the before and after table, just like we did in the last video. So on the next slide, we'll set up the before and after table. I'm just going to fill it all out, and it will already be there when you get to the next slide. Now remember that we must use moles in one of these tables, and so we have to multiply the molarity and volume to get moles for the acetic acid and for the hydroxide ion. The acetic acid, that came from the 50 milliliters of 1 molar acetic acid solution. The volume is 50 milliliters, or 0.05 liters, and it's 1 molar acetic acid, so times 1 mole per liter, 0.05 moles of acetic acid. For the sodium hydroxide, we've added 25 milliliters of 1 molar sodium hydroxide, so the volume is 25 milliliters, or 0.025 liters, and it's 1 molar sodium hydroxide, so 1 mole of hydroxide ion per liter, 0.025 moles of hydroxide, and initially we don't have any acetate ion. So once again, hydroxide ion is the limiting reactant, and so all of it will get used up. There will be none of it left over after the reaction goes to completion. Therefore, we've used up all 0.025 moles of the hydroxide ion. That means we've also used up 0.025 moles of acetic acid, and we've made 0.025 moles of the acetate ion. When you add it all up, what you end up finding is after the reaction goes through to completion, you have 0.025 moles of the acetic acid. That's how much is left over. And you also have 0.025 moles of the acetate ion when the reaction goes to completion. So this is a pretty interesting point in the titration curve because the amount of hydroxide that you've added was just enough to consume half of the acetic acid. We call this the half equivalence point. So at the half equivalence point, you've used up half of the weak acid that you've had. And interestingly, when you use up half of the acid, you have a situation where the amount of acid left over is equal to the amount of the conjugate base that you've formed. That will have some very important consequences for us when it comes time to calculate the pH of the solution. Now we're going to rewrite the list of major species that you have in this solution after the reaction has gone to completion. You still have acetic acid left over. You still have Na plus ion because that was just a spectator. The hydroxide from NaOH, however, is gone, right? That was the limiting reactant. Water is always present as a major species in any aqueous solution. And in addition to that, we produced a new item on the list that we didn't have before, right? We made acetate ion in the reaction. Now, having done that, we're going to ask ourselves, is this a buffered solution? And because we see that we have a weak acid and its conjugate base as major species, we now have a buffer here, right? So it wasn't a buffer before adding the sodium hydroxide, but by adding the sodium hydroxide, we've made a buffer. And since this is a buffer, we can use the Henderson-Hasselbalch equation to find the pH. So pH equals the pKa, which is 4.75 for acetic acid, plus the log of A minus over HA. The A minus is the acetate ion, which is 0.025 moles. The HA is acetic acid, which is also 0.025 moles. So A minus 0.025 moles over HA, also 0.025 moles. All right, so I've mentioned a few minutes ago that at the half equivalence point, because you've used up half of the weak acid, you end up in a situation where the moles of HA end up being the same as the moles of A minus. And I mentioned also that that's going to have some important consequences for us when it came time to calculate the pH, and here's where that comes in. Since the moles of HA and the moles of A minus are the same, 0.025 over 0.025 equals 1. And the log of 1 is just 0. So that goes away completely. What you end up with is that the pH is equal to the pKa of acetic acid. The pH of this solution is 4.75. And this relationship that the pH is equal to the pKa at the half equivalence point will always hold true for any weak acid and strong base titration. So at the half equivalence point, the pH will always end up being equal to the pKa because at the half equivalence point, you will have left over the same amount of HA as you produced A minus. Therefore, at the half equivalence point, this ratio of A minus over HA will always be 1. The log of 1 goes to 0, leaving you with pH equals the pKa. Next, we'll take a look at the fourth and final point on our titration curve. Next, we're going to take a look at something called the equivalence point.